2 o'clock here. I think Miranda has a different time zone, right?
Yeah, I'm 1 o'clock at the moment. The clocks went back the other day, so.
Okay, so first of all, thank you very much all for being here. Thanks to EY for this, for supporting this course, and also to connecting us with Miranda now, and for this, what I believe will be very interesting presentation about Nightfall protocol, and possibly later on also discussion, not only on Nightfall protocol maybe, but also more broadly speaking about the blockchain in enterprise, perhaps. Also for the students, disclaimer, so this lecture is being recorded and it may be published at the website of the university. So please be aware of that. And regarding the questions, feel free to write it into the chat and we can go through it once Miranda is done with the presentation. She will have a couple of slides in the beginning, and then we'll go through some demo, and then we can jump into discussion. So, and also just to introduce, so as you heard already, so we have here Miranda Wood, who is a cryptography and blockchain researcher at EY in the UK, right?
Yep.
And we also have here our guests from EY in Slovakia, Mikuláš Zalaj and Stefan Mačica, who will probably join us in the discussion after their Miranda's presentation.
Hello.
So I think that at this point, Miranda, you are sharing the screen already, so I think we can start with the presentation now.
Sounds good. Thanks very much. Yeah, so everything's working and you can see that. I'll turn this off for the moment. Great. Yes, so I'm going to be talking about Nightfall. I'll just quickly introduce myself before. So, yeah, I'm Miranda. I work in the EY blockchain R&D team in the UK. I've been working here for about a year and a half, mostly on Nightfall. And before that, I did a master's in maths in Scotland. And before that, I did an undergraduate in maths. So I'm not too long out of university, I suppose. So if also at the end, if you have any questions about getting into blockchain, getting into the industry, feel free to ask about that. Right,
I think you could start with that. I think it's probably also interesting for all of us to hear. So feel free to tell us a little bit more about also your background and how you got into this.
Sure. Yeah, no, I can do that. No worries. Yeah, so I did my undergrad at Brunel University. I really liked cryptography and that kind of stuff. This was around 2014, 2015. So Bitcoin was like $100 maybe, something ridiculously small now. And one of my lecturers had an interest in blockchain, and I did a dissertation with him. So I did a blockchain dissertation, and I really, really liked it. I think now, obviously in computer science, there's got to be actually more relevant stuff for you to do. I was just doing pure mathematics, and I managed to get into blockchain kind of by chance. So yeah, I did that, and then I really, really liked cryptography and blockchain, so I decided to do a little bit more study on it. I did a pure maths course, a master's, but you definitely don't need a master's to get into this industry. It's just something that I wanted to do. I did a little bit more about cryptography and some of the interesting stuff about elliptic curve cryptography, and came out of that with a dissertation. Yeah, I focused on elliptic curve cryptography and how it's used on blockchain, which is really, really interesting. And then I looked for jobs, and I saw that EY UK was hiring for a blockchain cryptography researcher, which seemed really perfect for me. So I applied, I had a really good interview, and it went well. I think, yeah, I think it was part of it at the right time, but also partly all my study had really, really prepared me for, I'd done a little bit of coding, I'd done quite a bit of maths, for balancing those things together to make a career out of it, kind of thing. And obviously, if you want to be like a blockchain developer, do more of the coding side, you won't need the really complicated maths behind it. That's the kind of thing that I guess researchers like me would do. If you want to be a developer, you don't need that kind of really, really complicated knowledge. You just need to be a good developer, a good problem solver. So yeah, I think that sort of covers most of my journey there. I can chat a bit more at the end if people have got questions. But I guess, should we get started?
Yeah, let's go.
Cool, sounds good. All right, so as you may or may not know, on Ethereum, we use a token called ERC20, which represents a fungible token. It's just the code for a fungible token, which means it can be exchanged for Ether, for money. So yeah, you might know this already, but I'll just go through it briefly so I can compare it to what we do on Nightfall. So with an ERC20, if Alice wants to transfer some ERC20 token to Bob, she mints an amount with the ERC20 contract, which is publicly available on the blockchain. She tells it how much she wants to mint. It takes that amount of Ether from her. It makes a token that then belongs to her. And then whenever she wants to, she can come along and call the transfer function with that amount in it and with Bob's Ethereum address. Then the ERC20 will deduct that amount from her balance, add it to Bob's balance of ERC20, and then he can withdraw it for Ether whenever he wants. So that's how a regular ERC20 transfer works. I guess the problem with this, which a lot of companies and actually a lot of customers, is when you're buying something, when you're transacting with other companies, that this is all public, just from the nature of blockchain. Everybody can see how much ERC20 you have, who you're transferring it to, how much you have at any one time when you withdraw it. So it's all publicly known. And for companies and for a lot of people, they might not want their private financial information on the blockchain for everyone to see. So that's where Nightfall comes in. And Nightfall is a solution that allows you to transfer tokens like ERC20. ERC20 is one of the ones we support. I'm just using it as an example. And you can do that privately. And so you can transfer from one person to another, while what everyone on the blockchain knows is just that somebody has come along and called the transfer function. They don't know how much you've transferred. They don't know who you're transferring it to. So I'm going to talk about how we go from this regular transfer to one on Nightfall. So I'm going to start with commitments. So the thing with ERC20 tokens is that they're public. Everybody knows who owns them. Everybody knows how much you have. Everyone knows where they're going. So we can't use those ERC20 tokens in Nightfall just as they are. So essentially what we do is convert them into something called commitments. And we just do that with hashing. And you guys probably know what hashing is and how it works. But in case you don't, it's essentially like a one-way function. You put in some inputs, you put in a long string, you hash it, and it will give you a value that depends on those inputs, but you can't go backwards from that value and work out what those inputs are. But you can verify that a hash is correct by hashing something, and then the output would be the same every time. But yeah, you guys probably know that already. To make commitments, we use the SHA-256 hashing algorithm, just so you know. So instead of commitments, instead of tokens, what we use is we hash together the value of the token we want to represent. We put in there the owner's public key. This is not the Ethereum address. I'll get into that a little bit later. And we also put in there a random salt. This just prevents duplicates. So if Alice owned two ERC20 tokens and she wanted to make them into commitments for Nightfall, then if she just hashed the value in the public key and they both had the same value, they would end up with two of the same commitment. And that would be awkward because we wouldn't know which one was spent. So we just put a random salt in there to prevent duplicate ones. And we have the cryptographic public key. And what we just use is you get a secret key and then you hash it and you get a public key. And the reason we do that is just a lot simpler to go from this kind of secret key to a public key than an Ethereum secret key to Ethereum address, because we need to do a lot of complicated maths, which you don't need to know, but it does happen in the background, about how we prove that you own a certain public key. It also separates it from the Ethereum address. So if you're a company and you have different Ethereum addresses, you can use them in Nightfall as well, as long as you keep the cryptographic public key the same. That will become a little bit more clear as I go on to how Nightfall works. But yeah, so the commitments hide the secret values that you want to not show on the blockchain. That's essentially what happens. So this might be a little bit complicated, but I'll talk through it. So commitments are really useful for replacing tokens and hiding stuff that we don't want people to see. But we need to prove that the commitment has been constructed correctly. And we want to prove that in such a way that all the secret information, like the value, who owns the commitment, is still kept secret. And this is actually a really difficult problem in general, proving you've done a computation correctly without sharing any secret inputs. So here we use something called zero-knowledge proofs. So this is pretty complicated stuff, and it's pretty counterintuitive, actually, even to mathematicians, because we need to create a proof that everyone can verify and everyone agrees, yep, this thing's done correctly, without actually really sharing how you've done it or what you've done. So it sounds like it doesn't work, but it does. So a lot of mathematicians call it moon maths because it seems like it comes from the moon. It's so crazy, but it actually works. And this is the main stuff that I've been working on in Nightfall. So if you have any more questions, want me to expand a little bit more at the end, feel free. So yeah, I've tried to simplify this process as much as possible because you don't need to know this crazy moon maths to use Nightfall, but you do need to know what you need to send to the blockchain and why. So let's just have a look at that. So the main piece in the middle, this is the circuit. So this represents the computation that you're trying to prove that you've done. So here, let's say, for example, it would be a hash, because it's essentially what we're proving. So this circuit can, excuse me, represent a hash function, and it can show that you've proved it. It can prove that you've done this hash correctly. So if you pass in a number, let's call it x, you want to keep that number x secret, and you pass in something that you're claiming to be the hash of that number, and you pass the hash in publicly. The circuit will then hash x, it will check that it matches the thing you've passed in, and if it is, it will go, yep, that's correct, and that's all sorted. And so, yes, with a circuit, there is an intrinsically linked key pair. This is something really important in zero-knowledge proofs. So once you create a circuit, it becomes fixed. So there's a fixed set of constraints, which are like logic gates. So those logic gates, those constraints, are used to produce a key pair, proving key and a verifying key, which kind of do what they say in the tin. We use the proving key to make the proofs, and we use the verifying key to verify those proofs. And a little bit like hashes, I suppose, if you change the circuit even a little bit, the key pairs will look completely different. So it's important to keep the circuit fixed for what you're trying to do. The proving key, the one you use to make proofs, I'll go through the process of how you can make proofs in a second. This is very large. Even though it's just basically a long set of numbers, a long set of points, to represent points in the elliptic curve, it's actually, I think, it can be up to about 5 gigabytes, and it's just a list of numbers. That's how huge it is. But the verifying key is very small. It's usually a list of 5 points. So you can easily put that on the blockchain. It doesn't take up a lot of space. And you don't need that much to verify a proof. So all the work comes from proving, which is great for us because we want to be able to do a lot of work off chain and then prove that we've done that work correctly on chain, so that we can do as little as we can on chain to save in gas costs, so to save in network costs, and also to save in network costs basically, and to save some time on the blockchain. So what Alice needs to do to prove that she's made a commitment correctly is that she passes in all the secret stuff. So I put all the secret stuff in yellow. So the value, her public key, and the salt. She'd also put in her secret key to prove that she owns the public key. The circuit would then go through the process that she did to make the commitment. So hashing those things together, hashing her secret key to make public key, hashing all those things together, and it checks to make sure that the hash that the circuit calculated is the same as the commitment that she put in. And if that matches, the circuit uses the proving key and it goes, yep, that's all correct. And it gives Alice a proof. That proof, again, is quite small. It's a few kilobytes. It's a small file. So instead of submitting all her private information to the blockchain, what Alice can do is put the proof and the commitment to the blockchain. Because the commitment's a public input, it can work together with the proof and the verifying key to prove that she's done it correctly. So that might seem quite complicated, but hopefully with the demo it'll be a little bit clearer. And So yeah, I think we're ready to have a look at how a Nightfall transfer works. So let's say we go through the same process. So Alice wants to transfer some ERC20 to Bob, but she wants to do it privately. So let's say that she already has an ERC20 token worth with a value of 10. Let's say she's got 10. So we need to make a commitment. So we have the functions with the same names, just to make it easy to see what you're doing if you're used to ERC20. Oh, and we use a contract called a shield contract. It's just called that because it shields the secret values within tokens. And then the F stands for fungible. So we have a fungible token shield. And that's just the naming convention of the contracts we use. For other tokens, we have some non-fungible tokens we support as well. So we use different token shields for this. But for now, let's continue. So she has ERC20 token of value 10. Let's say she wants to make a commitment. So off-chain, she will generate a proof that says, I have a commitment of value 10. This is my public key. This is the salt. And this is the amount that goes in it. And the proof puts all that stuff together. And it says, yeah, she's done it. But it doesn't actually reveal anything secret at all. So to the blockchain, she sends that proof. She sends the new commitment she's made. And she does have to send the amount. Now, normally we would want to keep this secret, obviously. But because we are representing ERC20 tokens, just with the way the blockchain works, there's no way that you can hide interactions with the ERC20 contract. So with this, the shield contract will look at the proof and the commitment, and it will say, yep, this amount corresponds to the commitment and the proof, and everything's done that correctly. So I'm going to withdraw this amount of ERC20 tokens into my big pool of tokens in the token shield. And the more people that interact with the shield contract, the bigger this pool gets, the more transfers are done, the more privacy is achieved, basically, because we have all kinds of people calling these functions, and especially with transfer, we don't actually know what they're doing, how much they're transacting with, who they're transacting with. So let's take a look at transfer and see how that works. So now she has a commitment of value 10. She wants to transfer it to Bob, but she wants to do that privately, so the observers don't know how much she's transferring and who she's transferring it to. So for example, let's say she transfers 5, because then that hides the value a little bit more and nobody gets to know the value of what she's transferring. So off-chain, what she does is that she proves she owns her commitment, that it has a value greater than 5, so that she can afford it. And she creates a new commitment of value 5 that belongs to Bob. So this has Bob's public key in there, and it has a new salt in there as well. And with the circuit, it works out all that stuff as well. And the proof says, yep, she's done that all correctly, and she intends to transfer this commitment to make a new commitment that represents Bob's new token, and she's done that correctly. So that's all we need to send to the blockchain: the proof, your commitment, and the new commitment. The shield contract takes the proof. It's got the verifying key in there. Sorry, I should have said that earlier. It uses the verifying key, it verifies the proof, and then it releases that new commitment, which belongs to Bob. But observers don't know that belongs to Bob. All they know that it's a long hash number. All they know is that somebody with Alice's Ethereum address called the transfer function with the proof and 2 hashes. That's all they know. They don't know who they belong to. They don't know how much has been transferred. They don't know anything like that. So if you're transacting with someone on the blockchain, you probably are already in contact with them, through email or something, through businesses. So Alice will be able to tell Bob, hey, I've transferred you this money. This is the commitment. And so Bob could withdraw. So what he does is he takes the commitment that Alice has sent him, because this has Bob's public key in there. He's the only one who can put his secret key into the withdraw circuit. The circuit hashes that to make his public key. It hashes that with the amount and the salt to make the commitment, and it verifies that he's done all that correctly and he does indeed own this commitment. That proof gets sent to the blockchain, and if he wants to withdraw, say, 3 of the 5 that Alice sent her, he can just put the amount 3. The shield contract will verify the proof, so everything's fine, and then it will interact with the ERC20.sol to transfer from the contract, not from Alice, from the contract some ERC20 tokens to Bob of that value. So all we know is that Bob has withdrawn 3 ERC20 from this contract. We don't know where it came from. We don't know how much Alice has. We don't know actually how much he owns in total, because he's only withdrawn 3, and so he would have 2 left of the 5. But that's still hidden in a commitment sort of floating around. So the more people that interact with this, the more commitments that we have sort of floating around, and all the observers know is that people are interacting with it, but we don't really know what they're doing with them, which is kind of exactly what companies want when they're transacting on the blockchain. And they're okay with being able to withdraw a certain amount of ERC20, because at the end that means their business is finished. It's all transacted and done. So yeah, that's how a Nightfall Transfer works. Might be a little bit complicated, but hopefully the demo will clear that up. So let's move on to the demo. All right. So hopefully you can see my browser now, and this is where everything Nightfall's kept. So this is all open source. So if you want to at home, you can go to this address. There'll be a link in the presentation as well. github.com/eyblockchain/Nightfall. It's all open source, so you can do this at home. You may be familiar with GitHub, probably, and you can clone this on the command line and copy all the code for yourself. So let's have a look at what that looks like. I just use Atom as an IDE, but I'm sure you guys at home have your own preferences. This is just what it looks like. So there's a big README, which is very, very useful for setting up at home. There are a few steps you will need to go through, some things you need to install, which I won't spend a lot of time on here because you can read it yourself. But there's a couple of important bits. So with Nightfall, to use it as I've described, this works on Mac and Linux machines with at least 16 gigs of memory. So I know that's quite a lot. That's basically for the huge proof sizes, for the huge proving key sizes that we have, and a lot of complicated maths in the background. But if you don't have a machine, or if you can't use a machine that handles this, don't worry, because you can still take a clone of this and take a look at how everything's set out. And you can take a look in the code to see how the test works. I'd also recommend, actually, if you're able to, sorry about the fast scrolling, for zero-knowledge proofs, we use Socrates as a kind of back-end package. And these guys have made an open source zero-knowledge proof service, which is really nice and easy to use. And it doesn't require quite as much memory as we need. It's quite a bit, but not as much memory as we need. So you can go there and you can start creating your zero-knowledge proofs. They've got some great tutorials. And you can use verified contracts, smart contracts that they provide to interact with those on the testnet on the blockchain. So that's also something you can do, and very useful for your learning, and it's quite fun, I think. But I'm a weirdo who did 2 maths degrees, so don't listen to me. Let's see. And where were we? All right, so you'll need a few things to install. Yeah, again, you can do this at home, but you will need Docker, Python, Node, and if you're using Mac, the Code command line tools. So Docker, by the way, I'm not sure if people are familiar. It's we essentially use it like a VM. So it will set up all sorts of containers with all the services we need to make Nightfall work. So we'll use it for the zero-knowledge proof service. So with Socrates, that will be one container, and then we will have the blockchain service, and we'll also have a Merkle tree service that we use for storing all the commitments. I don't have a huge amount of time to go into that, but at the end, I can go into how we store commitments, if you like, in the questions, because I spent quite a bit of work on that, so that's also something you can use at home. Yes, so we use Docker. You can clone the repo. This is all in the README. For Mac and Linux, you need to do some setup stuff, just permissions, so that the shell scripts will run. And here we go. Okay, so the first thing you'll need to do, which is interesting, I guess, is to generate a trusted setup. So ignore this for a second. And I've done this already, but let's see. So what that will look like is this. So to generate the trust setup, this is the process where you want to generate the keys. So actually, let's make this a little bit cleaner so it's more obvious what I'm doing. So to generate the keys, so we already have the circuits all written for you, but we just need to generate the keys, so the proving key and the verifying key that I talked about already. So I'll just go through the process of how that works. So you just put in the shell script Nightfall generate trusted setup, and it'll ask you a couple questions. So the first one is, do you want to use mimic hashing? I'll just very quickly talk about that because most of the time we use shell hashing, which is very fast on blockchain, but it's very slow in terms of zero-knowledge proof stuff and the stuff in the background. So it's kind of a trade-off. So if you want the zero-knowledge proofs to run a little bit faster, you can use mimic hashing, but that will cost you more in gas on the blockchain. So for businesses especially, it's a bit of a trade-off. If you just want to use Nightfall at home, it's probably best just not use it and see how it works, kind of plain vanilla Nightfall, so to speak. So let's put no in there. Then it will ask you if you want to use the compliance version. So this is something that a colleague of mine developed. So he basically made it so that if companies want to use it and they want to use it sort of internally, there is a way for admins to actually decrypt and find out what's inside commitments. But this is just for sort of private use, and the real value of Nightfall, I think, comes from when we use it publicly and you have your commitments completely private and only you ever know. Only you ever know them and only ever you can spend them. So let's go know that. Well, it's also a little bit slower because of all the additions. So let's select no there. So what you want to look at is this part here. So these are all the circuits that we have. So the examples that I've gone through are fungible transfers, simple fungible transfers. So what we want to focus on is the ones beginning with FT, because those just represent fungible tokens. The trusted setup does take a long time. So if you want to try this out at home, it's probably best just to go for the usual mint, transfer, and burn. So you can go through the example that I gave. So you would do, no, I don't want to do all the trusted setups. And you would just put the numbers in of each one, and it would just do this for you. So you would do 2, 3, and 4. So this takes a long time. I've done it already, so I won't run it here. But I'll go through these. So batch transfer, that's something that we made so you can transfer a lot of commitments at once if you're a business. The next 3 I've been through. So this burn is when you want to withdraw a commitment and get some ERC20 back. The mint is when you want to create commitment, and the transfer is if you want to transfer commitments between each other. And the 3 at the bottom are for non-fungible stuff. So that's for different types of tokens on the blockchain. So yep, if you want to go through this example at home, probably best just to do these 3. And this will still take a little while. I'm using a new MacBook, and it still takes me probably about an hour to do all of these. It does take a long time. It's just because of the really complicated maths in the background. It needs to construct that proving key, which is intrinsically linked to the circuit. So it's very, very complicated stuff going on in the background. It will take a while, but I have done this already. So I would suggest if you do this at home, just go and have some lunch, have a tea while it's working, and then eventually it'll be done. Don't worry. All right. So once you've done this, we don't need to worry about reinstallation because this will be your first time. We're ready to start. So all we have to do is run Nightfall. And again, this does actually take a little while to start. So I've done one already. That's what this one is. And there's a lot of logs. So sorry, this is very ugly, but I will get back to this. And then what we need to do is go to our browser, and we have a lovely UI, which I didn't build, so I can't take credit for. We do. So all we want is to go to the local host with the port 8000. We start it up. Okay, great, it works. So this is our local version of Nightfall that we can interact with in the browser. So let's see. If you're using this at home, you can literally just put anything in here. This is just an example, so you can just put A for all of them. Oops. And that will work, and it will actually create the account for you. So I've already made some for Alice and Bob. So let's log in. All right. So this is UI of Nightfall. So these 2 columns on the left are to do with non-fungible tokens. So I won't go into those right now, but these 2 on the right are fungible. So that's what we want to talk about. So on the left is what we're going to do to make ERC20 tokens. So this is stuff that will be public, but we need those to convert them into commitments that are here. We just call them OpsCoin as a kind of internal EY thing for demo purposes. But this is ERC20, and these ones are the commitments I was talking about. So to go through the example that I did, let's mint. This again is on a testnet. It's all happening on a testnet in the blockchain. So you can mint as much as you like. So we can go crazy and we can mint 50 ERC20 tokens. And that's done. We don't have to do anything zero knowledge proof E. There we go, that's here. So it's very quick. So now let's mint a commitment. So let's see, Alice has 145 available. Let's see, we want to transfer 10 to Bob. So let's do one of 20 and then we can keep 10 as change. So I'm going to mint a commitment here. And that's on its way. I'm going to do another one as well, just to show you how it works. All right, so now I'm going to get back to the logs. So the logs, when you run /nightfall, it's going to give you a lot of logs and more than you ever need. And this is just for sort of debugging. But the main thing that probably useful for you guys to look at is what's under the category of ZKP. So ZKP is a container where all our interesting zero knowledge proof stuff happens and all the stuff that gets sent to the blockchain eventually happens. So we have a lot of stuff happening here with, so Ganache is one of our Ethereum clients that we use. We also have Mongo for database, that kind of thing. But ZKP is the interesting stuff, so to speak. So when I press that button, it sends a mint request, basically. It puts together all the things that we're going to need to put into the circuit to create a proof. Sorry, this might be a little bit small. And now it's gone slightly crazy. Excuse me. Come on, go down. Okay. This is just some work I was doing earlier. Very sorry. I just tried to zoom in and it didn't work. I knew something like this was going to happen. Right. So while I'm talking and going through this, here we go. And here we are. All right. Sorry about that. So here we are in Mint. So these are the things we send to the circuit to create the proof. And the proof will show that we are making this commitment with however much the value was. I think it was 10. And we compute it using our Socrates backend that I talked about earlier. And we have the proof here. So that goes through. We then send that to the blockchain. So we send the transaction and we get the transaction receipt back. So it must have gone through and everything's worked properly. So now the shield contract, our token shield, has a commitment in there that belongs to Alice, but only Alice really knows that. And we did another mint as well, didn't we? So I'll scroll down. This is just stuff to do with the Merkle tree, which again, I can talk about later if there's time. And then we have mint complete here. And it's going a little bit more, and mint complete here. So now Alice has, okay, let's do an example. So this one starts with 0xEE. Let's go home. Look at the commitment she has. And there we go. There's that commitment there. So the UI is quite a simple way to interact with it. And then the logs that you will see in the command line are all the details, everything you will ever need, basically. And we also have stuff like integration tests, things like that you can interact with directly from the command line. These take a little bit longer to set up and there's lots of instructions in there. So for this demo, this is nice. So let's do a transfer. Go on the transfer commitment and let's select the two that we have. So we need 2 as an input because this basically, well, a couple of reasons. First of all, if you don't have enough value in one commitment, if say she wanted to transfer 30, then obviously she'd need both to add up to that value that she has. It also helps hide what's happening with commitments on the token shield, because the more commitments that are sort of added to this transfer function, the less likely you want to know exactly where they've come from and what's happening, that kind of stuff. It's also a little bit easier in terms of the circuit, because as I talked about, you have to keep the circuit static, you have to keep it the same in order to get so that the proving keys and verifying keys don't have to be changed every time you do something. So if we have a circuit that accepts 2 commitments, we can't change that circuit to accept just 1 without having to go through the whole setup again. So there's always 2 as input, but don't worry, we're only going to transfer 10 and we're going to give that to Bob. So let's start that off. So this does take a little while and the logs will go a little bit crazy, but it will happen. Here we go. In transfer. So this is where it starts. So it does simple stuff like finding the shield contracts, finding the verify contracts. Whenever it's talking about leaf, it's talking about the Merkle tree. So it's where we store commitments. So whenever it says checking leaves, inserting leaves, it just means we're checking whether commitments exist in the database and on the blockchain and that they're there properly. So we're doing some stuff with the Merkle tree here. And finally, we should get somewhere to set KP. All right, so we are double checking more with these here. And let's get to some interesting stuff, please. Here we go. All right. So starting here, we have some inputs to the proof again. So these are, again, a little bit complicated. It's kind of crazy how much complication goes into making this private, but that's the nature of zero-knowledge proof, nature of moon maths. So Alice has put in her input commitments, and like I said, she's going to get output commitments. So one of them will go to Bob. That one will have value 10. This is all in hex value, by the way, so that's why it's not in decimal. And one of them will go back to host change. So I think those added up to 40. So yeah, she will get a commitment back that's worth 30, and Bob will get a commitment that's worth 10. And all the observers looking at the blockchain will know is that she called the blockchain, she sent in proof, and her old commitments and the new commitments. That's all they're going to know. So this will be Bob's public key that she knows. And then we have all the information that will allow us to reconstruct those commitments inside the circuit. And as long as all those commitments match the input ones she's put in, the proof will be generated and the transaction will go through. So let's keep looking down here. So this, if you're going to use Socrates, we actually decided to put this here. So if you have a Socrates container, if you followed the link that I said before, you can use Socrates at home and you can copy and paste this little bit here and see exactly what happens in the background with Socrates if you're more interested in what the zero-knowledge proof style stuff happens. And we're computing the proof and we get a proof out. So that's great. That passed. We then send it to the blockchain. We get a receipt. It's all gone through. And then the Merkle tree will do some stuff to add the new commitments there. And we have transfer complete. So that did take a couple of minutes. Let's click here to refresh it. So we can see now that this transfer is complete. So what happened here was Alice used her 2 commitments. Remember the one starting with E from before. So everyone on the blockchain, all they saw was her putting in a proof, putting in these 2 numbers, and then getting these 2 numbers out. So this one here belongs to Bob, but only Alice and Bob know that. So the outside world just sees this number. That's all they see. And she gets 30 back in change. Now, again, because this is just working with commitments, we're not working with ERC20, the values here are actually completely private. So these 2 commitments here are now basically in the bin. They're not used anymore because they've been converted into these 2 commitments. And the outside world doesn't know what the value of these. All they know that is, yep, these values and who's called it. So if we want to, Bob can then burn a commitment. So, oh, sorry, Alice can burn a commitment. We're on Alice's account here. So let's say that she wants to withdraw all of this. She wants to get ERC20 tokens back. And she wants to just remove this commitment completely and just have 30, and ERC20 token value 30. So we do burn here, and that will go through the same thing. I'll keep the logs up here, but that's pretty much where I'm up to, and you can see them running. But we can start with some questions or discussion, if you guys like.
Thanks a lot, Miranda. It's, as you said, really moon math.
Yeah, it is. Yeah.
but it's indeed very interesting. Could you maybe just like zoom out and tell us like where is this currently being applied, in which use cases, or like what is the state of the protocol?
Sure, yeah. So we use Nightfall, I think, primarily in our tax team. So I don't know exactly the protocol, how they use it there, but the main thing about our protocol is that we can basically put a shield around what is happening on the blockchain, but still have people transfer and transact with each other without anyone being able to commit fraud or anything like that, thanks to zero knowledge proof. So our tax team use it to, instead of transferring ERC20 tokens between companies and then needing to share it on the blockchain so that they can be taxed properly on the value of those ERC20 tokens and the value of their business, they can instead use commitments. So they transfer commitments to each other so the outside world doesn't know all the private financial information, but then they can use the zero knowledge proof angle of it to prove that the amount of money that they're telling the taxman is in those commitments and they've spent those without revealing that to the world, but still transacting on the blockchain so that you know that no one can commit fraud and you get all the benefits of transacting on the blockchain. So having the records there for everyone to see, but not having everyone see the private parts of it. And I think, that's how the tax team use it. They're also with our non-fungible tokens. So we can use the same thing, but for non-fungible tokens that aren't worth money, but just represent something. So we do this, for example, with procurement, with moving goods around. So you can, instead of sending money to people in commitments, you can send things like a goods received note, which says, I've received the goods that you've sent me, and I verify that, and that goes onto the blockchain as a commitment. So the outside world doesn't know what that means, but the people who are transacting with each other do know what that means, and they mean, okay, goods received, that's great. So that's the kind of thing we're using Nightfall for right now.
Yeah, that was my question I wanted to ask. Like, so we're talking about ERC20, but now the whole world is hyped about ERC721, right? And the NFTs, so if there's no question if it's compatible with that smart contract standard as well, or if it has been used, for example, for some digital art transactions or something like that.
We haven't used it for any of the huge digital art stuff yet, no. But it does support ERC721, so that's sort of the main secondary token that we support. So obviously these days there's a huge amount of hype around it representing pieces of art or unique pieces like that. But we generally used it for relatively boring stuff so far, like goods received labels and invoices and stuff like that. So it's pretty boring, but we could definitely use it for something like that. Yeah, there's nothing stopping us.
So just to get back to my previous question, so now it's mainly used by, you said, like corporations that are exchanging ERC20 tokens. So is it perhaps applied somewhere in some of the DeFi protocols, maybe? Do you know?
I don't know actually, because it's open source, so anybody can actually come along and use it. And we are working a lot in DeFi at the moment, but not necessarily with Nightfall. We still have yet to bring those two things together, but that is something that we'd really like to do. Right now, I think I'm allowed to say anyway that we're working on a new version of Nightfall that uses an optimistic protocol. So it means that you don't have to send a lot of stuff to the blockchain all at once and cost a lot of gas, because recently ether prices, gas prices have risen up a lot. So we're trying to address that problem with an optimistic solution. And that's what we're working on right now. So in the next few months, we'll probably release Nightfall Optimism. And that's the main thing that we're working with teams with DeFi. Yep.
That's cool. Like, that brings me basically to two questions I had prepared for you. One is, and correct me if I'm wrong, I remember like probably, 2 years ago, I think when the Nightfall was released for the first time, I remember then there was the version 1, I think, and then like a year later there was a version 2, and there were like huge improvements in terms of performance, or like how much data you had to use to commit to the blockchain. So it was so can you maybe describe like how was this, where this optimization or this boost in performance came from, and maybe how the protocol evolved compared to the first version?
Sure, yeah, because it was actually released before I joined UI. I think it was version 1 or 1 point something when I joined, and now we're way ahead of that. So one of the things that I worked on that I touched on briefly was mimic hashing. So we used to use SHA-256 for everything, which is fine because it's very efficient on the blockchain, and to do any computation with hashing on the blockchain is pretty cheap. SHA-256 hashing, I mean. But in terms of zero knowledge proof stuff, mimic hashing takes a long time to set up. So the proof size, it requires more constraints if you use SHA hashing in zero knowledge proofs. So it takes a long time to set up. You have huge proving key sizes. And that was a bit of a pain point for people who used it. So one of the improvements that I worked on is having the choice to use mimic hashing. I think some people call it MIMSI actually. So you may have heard of it as MIMSI, which is much more efficient in zero knowledge proofs. So that brought our constraint sizes way down, proof sizes way down. It's a lot faster to set up and create proofs, but it does cost more on the blockchain, unfortunately, because there just aren't those efficient kind of pre-compiles that are already there. So there's a bit of a trade-off, but that's one thing for those people who used it who didn't mind how much it costs, but they did mind how long it took. So that's one improvement we made. Then one of the next ones I worked on was batch transfer. So instead of transferring one at a time, you can transfer up to 20. And so instead of just sending one commitment to the blockchain, if you want to transfer one commitment, you'd send 20, which isn't that huge of a difference when you consider that before you'd have to make 20 individual proofs that would have the time to go through it. You have to go through 20 different verifications on the blockchain, which is the most expensive part, is going through the verification maths. So being able to do that all at once is one of those things that, really helped people who are using it. And I think that's the main things we've improved on.
Okay. Before any curious students will ask questions, because now is the time. I have one more. So you mentioned you guys will be working and implementing this in optimistic rollups. So
yes.
My question was like, how is this applicable or interoperable with first layer 2s, but that's kind of answered, and then perhaps the future version of Ethereum, like Ethereum 2.0, and perhaps some other chains that copy the Ethereum virtual machine?
That's a good question. But we are working right now to be able to make this optimistic version basically a layer 2 solution. So it'll be compatible with layer 2 there. With Ethereum 2.0, we're watching it closely and we're trying to build it as much as possible. But to be honest, with Ethereum 2.0, it's changing so quickly in what's happening. So it's hard for us to be able to build the back-end zero knowledge stuff, which is really mathematically heavy, and kind of match it to what is happening right now. But the layer 2 solution we've taken a little bit of inspiration from ZK Opru, ZK Rollup people, and Optimism, and we've been talking to people involved in that as well. One of the scientists there goes by Barry Whitehat, who we've been working with in the past as well. And we've been building this optimistic protocol with the help of him and others. So we can hopefully get it out and it be a huge improvement on what we have right now. I hope that answers your question. Probably a little bit vague.
Okay, so you answered the first and second, and the third one would be like with other chains.
Sorry, I forgot about that. Yep. Right now, we're just focusing on Ethereum simply because as I said before, with the Shield contracts, a lot of the privacy comes from having lots and lots of people interacting with it. So, if one person makes a commitment and then nothing else happens, and then they transfer it and one person withdraws it, you can kind of guess by looking at it, okay, that's probably A to B. But if there are like 100 people interacting with it, it becomes very, very difficult from just knowing the commitment hashes, what's happening. So the more people that are using the blockchain that we put it on, the more people that are using the contract, the more private it is, and then the more people are likely to use it. So right now, we don't have a huge amount of plans to go on to smaller blockchains, But we have been looking at the MENA protocol, for example, is one of them, where we have public blockchains, see if we can adapt what we do and deploy that on there as well. But yeah, right now we're sticking with Ethereum just because it's a huge amount of people working on it, really.
Yeah. Okay, I think my colleague Christian maybe has some questions too.
Yep, thank you very much, David, and thank you also, Miranda. I have some questions. I saw that you are using Socrates for zero-knowledge proofs and the part of the solutions, which Socrates is considered secure, but have you been considering also some security analysis of the whole ecosystem of Nightfall, or are you thinking about that in the future? Because I didn't see any audits or security things that if you can really prove that Nightfall will be secure for anyone for the future use and so on.
Yeah, fair enough. So with Socrates, we use a proof system called GM17, which we consider to be right now. Yeah, there's a trade-off between it's quite efficient and it is secure. So there's another proving system called Groth16, which does actually have some security issues with it. So we moved away from that some time ago to use the newer one, GM17. What we can say is that the underlying proofs, we know that these parts are secure. So if you create a proof with a transfer circuit and you use the correct keys, we know that this is secure because of the mathematical work we've done and the work we've done with Socrates. It hasn't gone through something like a security audit from an external company, so we're not allowed to say that it's like secure for everyone because we need to have an external company come along, and with EY, it's being a big company, so we need to have someone else come along and do that. But we have been considering the security side of the mathematical side. So like I said, the GM17 proof system we use, the mathematics we do in the background, the kind of checks we do, especially with the way we store commitments with the Merkle tree. We actually use something that we built, something called Timber, which is an application that stores commitments in a big Merkle tree. And it helps you generate proofs that something exists in a database and exists on the blockchain. So that side we worked on pretty hard, and we're pretty confident with that one, yeah. Yeah, I hope that answers your question.
Thank you. And also regarding the commitments, is there any possibility to store them also off-chain, or are you storing them only on-chain?
Actually, we use a mix, yeah, because obviously storage costs on-chain, especially recently, have gone up quite a bit. So something that we do is we store a sort of fragment, like a fragment of the Merkle tree, which tells us everything that we need to know without storing every single commitment, every single leaf of the tree on-chain. So by storing the root and this fragment of it, we can kind of reconstruct the tree within a smart contract without having to store the whole tree. But we do store the whole tree off-chain. We just have to make sure that those are in sync, which isn't a huge problem. But so yeah, by doing that, we save a lot on storage costs. And yeah, that's all done through Timber, which is also actually an open source application that's, I think, linked to in Nightfall that students can go and look at too. So yeah, we use a mix.
So Timber and Merkle proofs work like a state channel or some channel which is off-chain, not on the Ethereum. Yeah, okay. And what about the transaction? You did a transaction from Alice to Bob. There is transfer outgoing 10 operation coins. Is this transaction already in Bob wallet, or does he need to interact with it somehow?
With this, yeah, he would need to interact with it because right now in the token shield, in the shield contract, all that anybody knows is that there's a new commitment. And Alice would have to tell Bob separately. I mean, if they're transacting with each other, they probably are in contact through email or something. They'd have to transact privately, and she would say, I've sent you a commitment with this value. And actually having that kind of private messaging can be quite difficult to set up. We used to use something called Whisper, but it wasn't updated very well, and there were some issues where we weren't sure how secure it was. So now we've decided to drop using that, and we're still now actually with the new optimistic Nightfall, we are going to use an encrypted messaging service that we're going to make ourselves. We're still working on that. So right now, yeah, so that transaction wouldn't be in Bob's wallet because we want to keep it private. We don't have anything to do with Bob's address or the value in there sent directly to him. But what we do want is for Alice to be able to tell Bob, I've sent you some money. This is the commitment. And then he can send a proof in and withdraw it without anybody knowing sort of which address that came from or where that came from, if that makes sense. So there's some issues with that, yeah.
Yeah, great. I'm really looking forward to that optimistic Nightfall. Do you plan to publish it also on GitHub as an open source, or
yes.
Will it be some? Okay. So we will see it someday. Yeah.
Yes. Yeah. We don't have a release date or anything yet. But yeah, anything to do with Nightfall, any upgrades, we'll always do it open source, so anyone can access it. Yeah.
Yeah. So maybe the base codes of the optimistic version are done proprietary at EY, but afterwards you will open the governance and decisions and so on through GitHub. Yeah. That is the future.
Yes. Yeah, that's what we plan.
Great. Thank you very much. I don't have any other questions, but students can ask also through the chat. So anybody?
I would maybe have a follow-up question to the one of Christian. So as you said that Bob would need to interact on chain and claim the transaction. Can you estimate, and just out of curiosity, how much gas that would incur nowadays?
That's a good question. I'll actually look through the logs and see what it says. This might be boring, but it has changed quite a bit. It used to be relatively cheap, but these days gas prices have gone up quite a bit. So let's see. So here we go. So for a burn, it's around 500,000 gas. So a burn is when Bob would interact with the blockchain and sort of claim that money back, as you said. So it's quite a lot, and most of that is taken up by the zero knowledge proof verifier, which we can't really avoid, unfortunately. It has some complicated maths that you do have to do on chain with the verifying key and elliptic curve pairings that you need to do. So one thing that we did to mitigate the gas cost of these proofs is to hash all the public inputs that you're putting together. So in this example, he'd need to put the commitment as public input. He'd also need to put the amount because he's taking ERC20 tokens back. And in some cases, we have more, especially with NFTs. So instead of putting all those in individually, we would hash them together and just have a single public input hash. So like here. And that saves gas costs because you send less stuff to the blockchain, and proving that those public inputs are correct happens inside the circuit, so it happens off-chain, and you just have to put in one public input. So that saved a bit of gas too. I think that's an improvement since release as well. But yeah, right now, especially with Optimism, we're working hard to try and get those gas costs down. So you wouldn't need to verify every single time with the optimistic Nightfall. So that's something that we're working on. But yeah.
Okay. I don't know if students have any questions at this point. Anybody, please feel free to raise your hand and voice. If not, I still have some in the pipeline.
Yeah, maybe if the students are afraid, they can also send the questions in chat. So don't be afraid. Just send the question.
So meanwhile, maybe I would also invite your colleagues from Slovakia to join the discussion, and perhaps even just speaking now more broadly, what are the, perhaps in your personal opinion, most interesting blockchain applications that in the enterprise environment that you work on in EY? Where do you see the most added value by the implementing blockchain?
I'll let those guys answer first, as I haven't had a chance yet.
Question on EY Slovakia, David, sorry.
I mean, EY Global, but you can, of course,
I think maybe if Miranda, if you can talk a little bit about the other, maybe not ZKP based EY applications. You know best what's new in EY network. Is that correct? Yeah. Thank you.
Yeah. No, I work mostly on ZKP, so I might be a little bit behind the times when it comes to this stuff. But I know that we do have a blockchain that tracks, how do you say it? Where something comes from. I've forgotten the word. But a blockchain that tracks wine in Italy. So it tracks it from the vineyards. Yes, provenance. Yes, thank you. Yeah, wine provenance in Italy, I believe. So we have that all set up so that consumers and companies can essentially scan a QR code and they can verify on the blockchain what is exactly where it's come from and its vintage and stuff like that. And you know it's come from the correct vineyard. Yeah, there we go. Awesome. It's one of those there. And that's been really popular so far, especially with traceability.
Yeah, this is from our latest or last presentation, and I think these four are the most typical use cases for blockchain, and at the same time, these use cases are EY applications. So what Miranda mentioned was the tracing the originality and the life cycle of products. Our Italian colleagues, they did it. They did an application for tracking wine. Other set of use cases is maybe represented by Tesseract, which is an application using blockchain to share resources, like, for example, cars, between the owners and the users, ensuring a fair proportion for costs and profit. Other use case, very big, was made together with Microsoft for Maersk. This is a specific class of use cases where many companies are interconnected via blockchain. Companies which otherwise don't share any information system and any common information security controls, and all those controls have to be in the paper world, made like in paper world, by signing documents and sending via post. And blockchain can play the role of big integrator of all those companies. And there is also a very interesting project, an application which EY made for Microsoft, which is very interesting also because Microsoft is the biggest software house, not EY, and still EY was able to deliver something very innovative to Microsoft, helping with sharing all the tantièmes between those people who participate on creating games for Xbox. So there are plenty creators like musicians, animators, and stuff like people like that, and all these people are waiting each month to get the correct payments for payments which are connected with how the specific game, Xbox game, is sold on the market. And the old way was using Excel spreadsheets and complicated calculations, and using blockchain and smart contracts is possible to share the provisions, the tantièmes online. Very interesting product.
Is this, and correct me if I'm wrong, is this related to the baseline protocol that it's also
probably. Yeah, as I understand, the ops chain and the baseline protocol are the platform on which all those supply chain based applications are built. Miranda, maybe you can explain more
Yeah, I believe so. So Baseline is a relatively new platform, but it's based on the Upstream platform that EY has always used for applications like these. And yeah, the EY built the original Upstream, and actually the R&D team, so not myself personally, but a couple of other people, developed some more sort of features for that. So there are some privacy zero-knowledge-proof features on there as well. And it's more recently been released as Baseline. And we're collaborating with people like Microsoft and Consensus to improve the platform further. So, yeah.
Okay, maybe like a kind of a meta question. Usually, and that's what I really like about EY's initiative in the blockchain space, that usually corporations and also Big Four, they work with private blockchains or work mostly on the private blockchains. So if you, I don't know if you guys have been involved or like if there is some internal discussion about these things in the company, in your company, and how it has been developed, and perhaps like if you're also active, if you work on some of the private blockchain use cases, or if you are solely focused on the public blockchain. That's my question. I don't want to take it. I think Miranda, you can.
I can
take it. Yeah, if you prefer.
Okay.
Yeah.
You can go ahead if you'd like. I don't mind.
Yeah. Okay. So maybe very quick introduction from Slovak perspective, but it is not very relevant what we are doing here. I mean, in terms of what is, for example, Miranda and their team doing. About 3 years ago, we had a client or two clients who were companies, startups, but already with relevant capital, I would say, startups, and they build their own blockchains, and of course they build private ones, or I would rather call it a consortium blockchain types. So we focused here in Slovakia to help the client logically to those blockchains. But then we realized that there are teams in New York, in London, in Germany, in Italia. There are teams of EY, people who are following the idea of building the blockchain applications on a public blockchain, which was very interesting for us. And we still were fighting for the private one or the consortium. But then afterwards we understood what's behind the idea of real the public blockchains, because you have at the end you have only one internet, even if it is connected through thousands of millions of networks. It is based on one common protocol, and this should be probably also the way for blockchain. It is imagine where it would lead if you will have different private blockchains, and then you will have to create an enterprise-wide information systems, which you would never be able to integrate if it will consist of different use cases on different private blockchains. So the idea of a public blockchain is a relevant idea, and we are very happy that Miranda and her team are doing this last piece. I would call it last piece, what is missing in a public blockchain, and this is the ensuring the confidentiality, because the other two elements of information security, meaning integrity and availability, is very good ensured by the public blockchain, by the elements which build the public blockchain. And the last piece is this confidentiality piece, which after we build, there is no question that the public blockchain should be the ultimate solution, I would say.
Sounds good.
Yeah.
Miranda, you want to add something?
Yeah, if you allow me to show you one slide, to add one slide, and Miranda, please correct me if I am wrong, because this is for me. This is not a technical thing, but it is very important. This one slide shows the information security assumptions, as I mentioned now, but this one is a very basic Alibaba cave It is an interactive
Okay.
zero knowledge proof protocol. Everybody knows, and everybody who not can find it in Wikipedia. But for me, what is important is this definition of a good blockchain, which is completely soundness and zero knowledge. And the interesting thing here is that this definition assumes some properties about Peggy and Victor, the prover and the verifier. And if you look at the definition, I think it is based on the assumption that the verifier is always honest. You can have a not honest prover, a cheating prover, but you have to have an honest verifier. And for me, this is the one thing which actually disallowed zero knowledge proof, because the idea is very old, or not very, but rather old, from last century. But only blockchain and the network of the provers, actually, the nodes, which can avoid that these automatically avoid or put outside the dishonest verifier, allowed zero knowledge proof to be used. So there is a symbiosis between zero knowledge proof and blockchain. These two technologies go very good together. This is what I find very interesting about an application of zero knowledge proof. I'm not sure, Miranda, if this is too naive theory, or
no, I think that's it's very interesting to me as well that zero knowledge proofs and blockchain they did develop separately. Obviously, it's been found now that zero knowledge proofs have like great applications for blockchain, so it's been developed more with a blockchain focus. But the two mathematical concepts were developed separately, quite differently, but they still have very similar principles running through them. So it makes sense that they'd be really, really great working together. Yeah, I find it super interesting, definitely.
Yeah, that would be perhaps my other question. Like, so Miranda, you having a background and practical experience with this moon math, what are the other interesting technologies, privacy technologies that you see in the realm of the public blockchains? Because I mean, we have a bunch of other protocols. I mean, including these Monero cryptocurrencies, or even the smart contract platforms like Secret Network and whatnot. So I would wonder, like, with your skill set and experience, like, where do you see the, what is interesting in your opinion out there?
Yeah, there's a lot of interesting stuff right now. I think it might be quite boring to a lot of people, but there's zero knowledge proof protocol called Plonk, which is actually looking really, really interesting in that it allows for, it's a lot of complicated stuff, but it basically allows for efficient recursive proofs. So you can prove something within a proof, which sounds a little bit crazy, but it's actually very useful. So, for example, with Nightfall, we can't hide that people are calling the transfer function because it's on Ethereum. So once you call the transfer function, everyone knows that they don't know what you're doing. They don't know what you're transacting or how much you're transacting, but they do know that someone with your Ethereum address has called that function. But with recursive proofs, it's actually possible, theoretically anyway, to do the normal transfer computation, like you've made the commitment correctly, do that proof, and then put that inside another proof, which says, I'm calling a function of one of these, mid transfer burn. I'm not telling you which one, but I'm calling one of them. And inside that proof are the inputs to the other one. So then instead of having to tell the world I'm calling mint transfer burn, you would just send a proof to the contract. It doesn't actually tell you which function you're calling. Right now, it's very slow. The proofs are very big, too big for the blockchain. But that's really interesting to me because you could just send a proof to this smart contract, and the proof would say you've done everything correctly, including all the transfer stuff, if that's what you're calling, and you're calling one of these functions, but you don't have to know which one. So the world knows that you've done it correctly, but they don't know what you've done. And it's very interesting seeing that mathematics work together. It's like, I don't know, Jupiter maths. Like this is beyond the moon for me. So it's very, very interesting to see those recursive proofs coming in. And it might be the future of private smart contracts, but we'll have to see.
Was this developed by Starkware in Israel, I think, or?
No, this one is maybe it was. But I know that they do Starks. They might be based on Plonk. But yeah, Starkware is also very, very interesting. They also do recursive proofs. We don't look them a lot simply because their stuff isn't open source, so it's relatively hard to access the exact mathematics behind it. But some things they have published, yeah, and they're very good. Plonk, I can't remember if it was developed by them, but you can find more information about it. It's open source and you can use it in your own way. So, yeah.
Okay. Maybe last question. There's okay. Many, I think. So like a few years ago, I was this kind of saying that the number of people that can understand the Zcash and zero-knowledge proofs, math, and cryptography it can be counted on one hand. Like, how has this evolved over time? Like, I don't know, like, how big is your team? How hard is it's hard for you to find new people who would have at least some, understanding of this technology?
Mm. It's still very small. It's larger, but I guess it's gone from one hand to two hands. It's still not huge, but the world has been growing. So my R&D team, so the people who work with zero-knowledge proofs, we have 5 people now total. And I'm not sure about other regions, but in the UK, we are the 5 people who do zero-knowledge proofs, and in EY, and that's it. And then the mathematicians who do the real background stuff that we end up using, there again are only a few. So like I said, we used a proving scheme called GM17. The G stands for Groth, Jens Groth, and the M stands for Mary Malla. And we've worked with both of those people. And I've met Mary Malla, and it's whenever you see a name applied to something as zero-knowledge proof, you'll probably think, oh, that's that guy I met a couple of weeks ago at the last zero-knowledge proof conference. Like it's that small, is what I mean. Yeah. So it's still small, but it's growing slowly.
Which brings me to this question, like, so in cryptography, everything that is, hasn't been battle tested for years, it's still considered very risky. And given the, like how few people understand it and how many people actually are able to audit these protocols, like, where do you think, how much time needs to pass that when we will be able to consider this to be really secure to be used in the public?
It's a good question. I personally find this quite hard to say because I think maybe because I'm a little bit modest, and if I build something, I don't like saying this is secure without having like 3 other of my colleagues looking at it. But it's very difficult to say because new attacks usually are found when somebody makes a proof system and they look at it and they go, it's pretty secure, but if somebody did this, and it might be broken by this, and the mathematicians who make it can often use it. But sometimes there are things that people discover later on, and it's very hard to predict this kind of things. I think there's something called Keon's attack, for example, CHEON, with the zero-knowledge proofs, when we have like a very, very large circuit with lots and lots of constraints, and once the constraints get higher and higher, you can actually do an attack called Keon's attack, which breaks it because there are so many constraints. I can't remember exactly how it works, but there are things like that are discovered, and I don't know if the zero-knowledge proof community is big enough for people to be able to spend all their time on looking for these attacks that they may not even know is there, if that makes sense. But then again, the mathematicians that are making up these proof systems, that are doing this stuff today, are good enough to recognize where there might be security holes in the protocol that they made, and they will say them, and they will say this is how you prevent them. So I'm not too sure on that, but I think there is still time to go for the community to get bigger. Yeah.
It's just interesting. Oh, sorry, Miklos, you want to say something?
Yes, a small remark. Even if the mathematical concept is correct and it is proved that it is correct, the implementation in software is very hard to be proved that the implementation is correct. So you will always have to calculate that there are some bugs in the software, And that's why you cannot talk about some bulletproof software solution of everything, including encryption algorithms. So you always need to view on a solution through a risk analysis. And here, if you compare, for example, the paper world and the signature made by hand with the digital signature, then you have a really huge difference. Of course, the electronic world and the digital signature has those inherent risks, which can be misused, for example, by the fact that you can do this in 1 second, a million or milliards signatures, which you cannot done by hand. So this is a difference. But if you compare the fact, that signature made by hand, it is nothing actually. And on the other hand, you have a very good mathematical model of a real signature. We should take into account this transformation in the first place, I think.
Yeah, Mickey mentioned it's not bulletproof, but bulletproofs are one type of the zero knowledge proofs, right? So can you, Miranda, maybe tell about those a little bit, like how they're different?
I don't know a lot about bulletproofs actually, but and I think one of the people who worked on it was Mary Mallow, was the person who did GM17. So the world is small. I don't know huge about those, unfortunately, but I know that they are designed to be very, very fast and have very, very small proof sizes, even smaller than the ones we use for Nightfall, which are already quite small. They use tiny, tiny ones, and the whole point is that you have a really big throughput and you can do something really quickly. So zero knowledge proofs, yeah, the world of zero knowledge proofs, people concentrate on different things. Some people concentrate on hiding as much as you can. Some people concentrate on recursive proofs, and bulletproofs is one of those things that concentrate on speed, because, as I said, even on my new MacBook, it takes around an hour to set up all the things that we need, which is, in the computer world today, is a long time. It's a really long time rather than doing something instantly. So I know that bulletproofs, I think, are one of the fastest out there. That's the name. So.
Okay, I think we are nearing the end of our session. Thank you very much, Miranda and Nicolas, for being here and sharing this knowledge with us. You definitely have satisfied our thirst for knowledge and curiosity. I hope it was the case with our students too. And thanks a lot once again. We will probably publish this lecture recorded somewhere on the YouTube, and we'll share it with you. And it was a pleasure to have you here, and hopefully we will meet again developing some cool stuff on public blockchains.
Thank you.
Yep.
Thank you very much.
Thank you very much.
Have a good day.
Okay, guys.
Thank you,
Bye-bye.
Miranda. Bye-bye.
Thank you. Bye.
Bye.